In this lecture, we will continue our discussion on supersonic wind tunnels. In the last lecture, we had initiated discussion about the intermittent blowdown type tunnel, and we had briefly looked at the different components which comprise the tunnel and the tunnel's utility. Remember that here we run the compressor, fill up the storage tank and keep it ready for a short blowdown or run of the supersonic tunnel, which may last only a few seconds. Very often for running it for a couple of seconds, you may need a preparation time which goes into a couple of tens of minutes or often few hours as well. It depends on how many compressors you have in the system, how large a storage tank system you have. Accordingly, the blowdown time gets decided. Further, the test section size will also be a factor in deciding it. So, the CD nozzle is located upstream of the test section. The flow accelerates through the CD nozzle from near stagnation conditions at the inlet, which is created at the settling chamber end. Because of the fairly high area ratio between the settling chamber and the CD nozzle throat, you can assume that the flow is almost stagnant at the settling chamber end before it starts accelerating through the converging section of the CD nozzle. So, as the flow accelerates through the CD nozzle from near stagnation conditions, what happens? It goes to sonic condition at the throat if you have appropriate pressure ratio, and further it turns supersonic at the exit for a correct pressure ratio. And when it turns supersonic, the flow is further let into the test section, which is the constant area section. So, this happens to be a constant area section. Now, you may recall that in an earlier lecture we had discussed in detail about different flow conditions at the exit of a CD nozzle depending on the pressure ratio across the CD nozzle. So, we will very briefly recapitulate that, because that is a very essential part of discussion of supersonic wind tunnel design. And then once we are done with that, we will discuss about the utility of a supersonic diffuser which is placed downstream of the test section and how that may enhance the efficiency of the supersonic wind tunnel. So, that is the portion which has a lot of impact in improving the tunnel efficiency. So, these are the figures which you may recall, where we had discussed about changing the back pressure or exit pressure and then trying to look at how it impacts the flow within the CD nozzle. So, we discussed about different possibilities. So, different pressures can create isentropic or non-isentropic situations, and here in the case of supersonic wind tunnel, we are of course interested in having the isentropic conditions through the CD nozzle, so that we have a very stable supersonic flow through the test section. We are certainly not interested in cases like this, where a shock might occur in the diverging part of the CD nozzle and thereby the flow turns subsonic downstream. This kind of situation will make the tunnel altogether useless. We might, however, look at situations where the shock is formed right at the end, not of the CD nozzle, but perhaps in some other section, maybe at the end of the test section itself. And by that time, we would have had a nice uniform supersonic flow within the test section. So, we will not mind. So, we will discuss about different possibilities in the upcoming slides, but the discussion will be very much based on the background that we achieved through the discussions which we are briefly recapitulating through these figures. let us look at a situation where we are trying to do an experiment where we can study the oblique shocks formed on a wedge like this. So, we need a supersonic flow in order to see that shock, and as I mentioned earlier that there are different optical techniques like Schlieren, shadow graph techniques, which we will discuss later when we discuss flow visualization, where we can visualize wave patterns formed in compressible flow by using optical means. So, hopefully, once we deploy those methods, we will be able to see this shock, but how can we get this supersonic flow at all? So, we start from a very rudimentary plan that we will have a nozzle, a CD nozzle exhausting directly into the atmosphere. We do not have a tunnel as such. What we have at this point is a compressor, a dryer, storage tank, the valves, the stagnation or settling chamber, and just a CD nozzle. That means, we stop here essentially. So, that is the portion we are showing over here. We do not have the test section, we do not have a supersonic diffuser further. What would be the consequence? Let us try to understand the consequence. Let us set a target of getting a Mach 2.5 flow over here. So, we will find that for this we would need an area ratio first of all, AE by A star of a value of 2.637. So, from area ratio equation you should be able to get this, and the corresponding pressure ratio to get this supersonic flow exhausting into an ambient pressure of 1 bar or 1 atmosphere is going to be 17.09. If that happens, then what do you have? You have a supersonic free jet exhausting into the atmosphere. Now, what is the consequence? The consequence is that you have to have a high pressure reservoir which can store the gas at 17.09 atmosphere, plus you need to have an appropriate compressor to raise the pressure to that extent, and then you may not be able to sustain the flow long enough also if it is an intermittent facility. So, handling these kind of high pressure, storing them etc., could be first of all difficult, secondly quite expensive. Before we move on, let us try to look at gas tables, because we have not looked at them earlier, just to get a glimpse how do we get these figures from tables of this kind. So, isentropic flow of a perfect gas with gamma equal to 1.4 corresponding to air is available in gas tables. So, if you look at such tables, we need it for 2.5, and what do you get from the P by P naught column? You get a value of 0.0585. You invert it, you get the 17.09 which we just quoted, the pressure ratio. So, that is how you will be using this table to get the values for different Mach numbers if you are interested with other Mach numbers. So, that is the solution we got with a free jet. However, we understand that for that you need a high pressure air supply at 17.09 atmosphere, which may be difficult to arrange, and you need not only high pressure air compressor, but high pressure air containers, maybe a bank of air containers if you want to make the run for a longer duration, and that really makes it very expensive. And usually the higher the pressure, the more the cost. That is how it scales. So, what do we need to do? We need to explore whether we can accomplish the objective in a more efficient way, that means at a lower cost. What is the immediate thought? The immediate thought is that let us not use just a CD nozzle, but attach a constant area section at the end of the CD nozzle. What could be the outcome? Remember that attaching the constant area section means you are getting closer to the full form of the intermittent blow down tunnel which we had sketched schematically. So, you are adding on the test section now, but you still do not have the supersonic diffuser in place. What advantage does this give you? It gives you the advantage of using this constant area duct to establish the uniform supersonic flow within which you can now put in the model, and then at the end of which you can say that I do not want to create a supersonic jet which goes into the ambient, but rather I would use a normal shock at the exit of this duct and then try to figure out what does it do to my pressure requirements. So, that is the question I ask. So, instead of the free jet, we are attaching a long constant area section which is more like the test section downstream of the nozzle exit, and then we are going to create a normal shock wave at the end of the constant area section. What is the outcome? Beyond the shock wave, we should restore the 1 atmosphere pressure. Remember that Mach 2.5 flow is approaching from the left, it crosses a normal shock and it reaches a pressure of 1 atm after the shock. So, region 1 is ahead of shock, region 2 is behind the shock. So, we just make use of normal shock calculations. Again, we can go back to our gas tables and look up the normal shock tables there for a perfect gas. Again, for air, from the tables which we will see soon, we can figure out that the static pressure jump across the shock will be 7.125, which means you can have a 1 by 7.125 atm ahead of the shock, because you get this much jump across the shock anyway. So, the pressure upstream of the normal shock now becomes 0.14 atm, that is a small fraction of the atmospheric pressure. And now, the advantage is that you are going to have the same flow expanded to a pressure of 0.14 atm at Mach 2.5, that needs only 2.4 atmosphere at your stagnation or settling chamber end instead of 17.09. So, what is the advantage you have gained? You have gained an advantage of a factor of 7.125. Who has given it? It is the normal shock which has given it. That is a huge advantage which we have already got. Let us briefly look at the normal shock tables. So, we go to the 2.5 row, and in the table we have the advantage of getting the P2 by P1. So, that gives you the P2 by P1 kind of ratio, and that ultimately gives you the requirement of 0.14 atm upstream of normal shock, which you need, and therefore, your compressor or storage tank requirement reduces to 2.4 atm instead of 7.09. However, there are some problems associated with having the normal shock at the end. So, you have a Mach 2.5 being slowed down, and the subsonic Mach number behind it will be 0.513, immediately behind the shock. Now, that is all fine, but what are the problems then? The normal shock is a very strong shock, and that creates largest total pressure loss. If we could replace the normal shock with a weaker shock, the total pressure loss would be still less, and the required reservoir pressure would be less than 2.4 atm. That means, though we are very happy that it is much lower than 17.09, but still this shock is a source of a large stagnation pressure loss. Can we reduce it further? Because that will have an implication in terms of the reservoir pressure. We can probably operate the same tunnel at Mach 2.5, but with still lower pressure. But what is the way out? We will look at it later. It is also extremely difficult to hold the normal shock stationary at the duct exit. In real life, the flow becomes unsteady. Instabilities cause the shock to move somewhere else and fluctuates constantly in position. So, the shock does not even stay still at one location. Thus, we could never be certain about the quality of the flow in the constant area duct, and that may put a big question on the quality of the results that you get out of the experiment. This is a very serious issue. Again, as soon as the test model is introduced into the constant area section, oblique waves would propagate downstream, causing the flow to become 2 or 3 dimensional, and the normal shock will not exist under such a flow, because the normal shock is going to exist only in a 1 dimensional situation. So, the moment you put the wedge model here, the wedge model generates oblique shocks, the shocks reflect from the wall and they make the flow very much 2 dimensional, or in the case of a cone further 3 dimensional and so on, while the normal shock typically exists in a 1 dimensional flow. So, there is a big question whether the normal shock will occur at all, probably not. So, it does not seem to be a very practical solution anyway. Is there a better solution? We move closer to a more ideal solution, which is usually used in supersonic wind tunnels, where a supersonic diffuser is used. That is what is going to bring us closer to this section, which needs to be further added. So, up to this we were looking at adding the constant area duct and then having a normal shock at its end, but we realized the difficulties. So, we are further putting on the supersonic diffuser. What is it going to do? It is going to accept the supersonic flow, send it through a converging section, then send it through a constant area section and then a diverging section. As it does so, what happens? The shock from the model, additional shocks which are created from the lip of the converging section, they get created, they reach the walls, they bounce back, multiple reflections are caused, but the flow is gradually slowing down, because as the flow crosses each shock, it is reducing in terms of Mach number. There are stagnation pressure losses, we accept that, but there is rise in static pressure and reduction in Mach number. Once the flow has slowed down enough, what happens at the end of this constant area section is a weak normal shock, and then finally the flow turns subsonic in the diffuser section here, which is actually a subsonic diffuser portion. So, this entire structure is called as a supersonic diffuser. If it was handling the flow in an ideal world, then what would have happened is that it would have taken a supersonic flow to a sonic one and then a subsonic one, but because of obvious irreversibilities and losses in the real world flows, we do not have such a solution available, but this is the best possible in such a situation. Now, when you progressively slow down the supersonic flow through a series of oblique shocks and you finally turn it subsonic through a weak normal shock, what happens is you incur lesser stagnation pressure loss than the huge stagnation pressure loss that a single strong normal shock can bring, and that is why it is a better solution than the one where we added a constant area duct and had a normal shock at the end. Additionally, we have more problems with the normal shock situation, which we discussed already. Now, the questions which still remains in this case is that what happens when you have so many shocks forming here anyway. There are losses which are incurred due to more extensive multiple shock wave boundary layer interactions. So, that still is a question, but that is generally outweighed by the benefit that we achieve through this setup. That means, we are hopeful that with this setup we will be able to reduce the pressure requirements even below 2.4 atmosphere. So, the requirement may be lower than 2.4 atmosphere, and then adding this supersonic diffuser portion is certainly beneficial. Now, we would try to answer one question, that how do we scale the throat of the supersonic diffuser? That is a very important question to ask and trying to answer it. Let us try doing that. We assume that the mass that flows through the choked throat of the CD nozzle, where you have the star conditions. So, rho 1 star A 1 star into the throat area of the CD nozzle decides the mass flow rate, and that mass flow rate is the same that will cross the second throat, that is the supersonic diffuser throat. But in all probability in a real world we will not have sonic conditions there. So, you will have the density and the velocities perturbed from the star conditions. So, we cannot really claim that these are star values really in reality, but later on we will probably bring in certain arguments where we try to go back to sonic conditions at both the throats and take the arguments forward. Let us see. Now, since the thermodynamic state of the gas is irreversibly changed in going through the shock waves created by the model and in the diffuser, clearly density and velocity at station 2 will be different from that at station 1. So, which we already argued over here. Now, we would then have to ask the question that how does this AT2 scale with AT1? Is it going to be greater? Is it going to be lesser or equal? How do we scale it? Now, we write down this equation, which basically comes from the mass flow rate equation itself. So, that is basically the continuity requirement, and then we put the argument that since we do not know what rho 2 A 2 is, let us begin by saying that sonic flow does exist even at station 2, and let us take it forward and see what comes out of it. Now, whether the flow is isentropic or not, as long as it is adiabatic, A star will remain constant. We have seen it from our earlier discussions, and flow across the shock waves is always adiabatic as long as you are not adding heat or taking away heat, etc. It is not isentropic, but it is adiabatic. Hence, the flow through the wind tunnel in general is adiabatic, even if it has shocks, which basically means that the A star at stations 1 and 2 have to be identical. What happens as a consequence? This becomes 1, and so you are left with AT2 by AT1 equal to rho 1 star by rho 2 star. Again, T star is also constant throughout the adiabatic flow for a calorically perfect gas, and therefore, if you invoke the equation of state now, what can you write further about rho 1 star by rho 2 star? So, according to equation of state, you write it in terms of pressure and temperature like this. So, it reduces to pressure ratio, and then if you combine the last two equations, this one and the one that we left behind in the previous slide, if you combine them, you will get an equation like this. Can we write down the P 1 star and P 2 star in terms of the stagnation pressure values at the corresponding stations? Yes, we can. We have learnt about these equations earlier. We can substitute them, and then what are we left with at the end? We are left with this equation, that the area ratio is equal to 82 by 81 equals P naught 1 by P naught 2. Now, in an ideal loss free case, what happens is P naught 1 is going to be equal to P naught 2. There are no losses, there are no shocks, and therefore, the pressures are conserved, the stagnation pressures are conserved. So, the flow nicely isentropically expands, turns supersonic, and again you can take it through a supersonic diffuser, it will again turn back to sonic condition and become subsonic, but that is in a loss free world. But in reality that does not happen, and we encounter an issue that P naught 2 in reality is always going to be less than P naught 1. The total pressure always decreases across shock waves. Therefore, AT2 is bound to be greater than AT1. That means, the second throat area is greater than first throat area. That is a very, very important finding. Only in the case of an ideal isentropic diffuser, where P naught is equal to constant, would these areas equate, but that is an impossibility. So, we are not discussing that in a real world. What happens if you do not maintain it? Then the tunnel tries to adjust and go to a different equilibrium, but then you have to have sufficient area available at the second throat, so that the tunnel starts appropriately. When you just allow the flow to come in, basically what happens is a normal shock forms, because there is a suddenly expanding flow moving into a stagnant region, and therefore, you have learned from the idea of shock tubes also that a shock runs from the high pressure region to the low pressure region, the driver to the driven section, etc. So, the same thing happens here, and the shock should be able to run through the second throat and get thrown away outside the tunnel. Only then supersonic flow is properly established in the tunnel, without which the tunnel will not start. We discussed quite a bit about intermittent blow down type tunnels, but they are not the only ones which are in use. There are facilities where you can run a supersonic tunnel for fairly long durations, at least not intermittently. So, we have just put together a small sketch of a continuous closed return supersonic wind tunnel. What you have over here, again the heart of the tunnel remains as the working section. So, what does it comprise of? You have supply of high pressure gas coming from this end. Let us say the stagnation temperatures and pressures are indicated as T naught and P naught. The flow moves through the nozzle blocks which form the CD nozzle. So, one thing that we need to note is that supersonic tunnels are built of metal, unlike many of the subsonic tunnels which are built of wood or softer materials. So, you have thick metal walls, and inside them you often fit liners, which provide you the advantage of achieving the contouring that you need for your nozzles. So, liners are fitted like this. So, these are separate metal pieces which need to be carefully manufactured, and then they are essentially fastened to the main walls of the wind tunnel. So, that is how they have been shown as nozzle blocks over here, and then you can figure out that the inner contours of those nozzle blocks are essentially giving you the contour of the nozzle itself. There are tunnels where these nozzle blocks are flexible. So, they are essentially made out of steel plates, and then these steel plates can be backed with hydraulic actuators, and when these actuators operate, they can push or pull the plate accordingly and therefore alter its shape. So, the plate can move depending on the actuation. So, there you can have variable sections created with the same steel sheet liners, but if you have fixed nozzle blocks, then this needs to be changed every time you change the test section Mach number. So, that is how it is normally done, but in certain facilities you also have the convenience of having flexible sections. And then you have the wind tunnel model with appropriate mounting, instrumentation, etc. Then as you can see the supersonic diffuser section which has been shown, and then because it is a closed circuit, you have the loop completed. You can see a dryer which is every now and then taking away a part of the flow and drying it up in case some moisture gets into the system due to minor leakages, etc. Otherwise, at the beginning of the run itself, the entire air confined to this circuit has to be dried before the run initiates. And then you can see that after the run the pressure changes, and though the stagnation temperature may not change significantly, once the compressor runs on it, it does work on the gas, the temperature will change. The pressure which had reduced at the end of the run due to irreversibilities is again restored by the compressor, but as the compression occurs, the temperature gets increased, which has to be reduced by passing it through the cooler. Therefore, you have to have a heat rejection here. So, work done here and heat rejection here. Finally, to restore the gas back to its original thermodynamic state, which you need to feed over here, and that has to be done on a continuous basis, because it is not an intermittent blow down. You have a continuous closed return supersonic wind tunnel. So, there are calculations to work out how much work done, how much heat rejection, etc., which are involved in the process, and once you put those calculations in place, you can do the design calculations accordingly to scale the tunnel. We will probably discuss about these aspects in brief in a later lecture. So, in this lecture we first recapitulated the flow through a converging diverging nozzle under different operating pressure ratios. Then we discussed about the utility of a supersonic diffuser in supersonic wind tunnels, and then towards the end we very briefly discussed about a continuous closed circuit supersonic wind tunnel. Thank you.